get started, I want to acknowledge that I stole lots of images from all over the web. I'm particularly grateful to people like Michael Zyla, Dan McGlawn, and Xavier Hubier, and others that have produced materials and put them on the web that make it really easy for me to be able to talk about this topic to the public. So let's start out by talking about what an eclipse is. An eclipse is just a shadow. The moon gets between us and the sun, and we can't see the sun anymore, but what it manifests as is a shadow of the moon on the Earth. So let's think about that in a little more detail. If we think about how the moon moves around the Earth, here I've got the Earth, and I've got the moon going around the Earth, and when it's in this position over here, it's a new moon. It's between us and the sun. The sun is somewhere off screen over here. We can't see it, that even though it's lit up on the side pointing towards the sun, that side is pointing away from us and we can't see it. And that's what we call new moon. As it moves around the Earth, we start to see part of that lit up half. So half is always lit up, but at this point, if we're standing here and we're looking at it, then there's only part of the moon that we can see that's lit up. As it moves further around, we get to see half of it, and then we get to see it waxing, and then we get to see it full. Now, this is a fairly simple picture, and we have a tendency to think in 2 dimensions. And so a lot of people will say, well, hang on a second, if the moon is going around, how do we see it when it's full? Isn't the Earth in the way and blocking it? And when the moon is on this side over here, a new moon, how come we don't get an eclipse every month, every time the moon goes around? And so I want to try and address that issue. So we tend to think in 2 dimensions, and we need to think in 3. So this white line here that says plane of the ecliptic, that is actually the plane made by the Earth and the sun. So in this case, the sun is somewhere over there, here's the Earth, and then the moon is offset. And so what happens is that this isn't as good as the one below. If we see here, we've got sunlight coming in, we've got the moon up here, and even though it's got a shadow behind it, that shadow is too high up, it doesn't hit the Earth. Likewise, when it's at the other side, it's now too low down to be blocked by the Earth, and so we still see it. And depending on where we are in our orbit, it might be below the Earth, it might be above the Earth, or it might be lined up. So you can see in this lowest scenario, we've got the sun is sending its light in here, there is a moon here, and now it's lined up, and so its shadow hits the Earth. And so this is the really important way of thinking about why we don't have one every month. But we do have one actually fairly regularly. It's just a matter of where. So here I've got the sun, and the Earth is moving around the sun, and so this big circle is the orbit of the Earth around the sun. And then we've got this tilted angle of the moon around the Earth. And you can see at this point, at new moon, the moon is too low down, its shadow doesn't hit the Earth, so there's no eclipse. But when we get to about 3 months later, remember, a full circuit is about a year, so about a quarter of a year is 3 months. We've got the sun, and the new moon is right in the path, and so now we're going to get an eclipse there. But as soon as we move away from that lining up, it's not going to hit the shadow won't hit the Earth anymore. So you can see here, another 3 months later, the shadow is way above the Earth, and we don't see an eclipse. But another 3 months, so 6 months since the last eclipse, we should get another one. Now, exactly how they line up, it's not exactly 6 months, and this has to do with how long it takes the moon to go around and how fast we're moving around the sun and so on. But basically, approximately every 6 months, we should have an eclipse of some sort. But in any given location, they don't occur very often. So they happen somewhere on Earth about every 6 months, not quite. Some of them don't quite hit. But that doesn't mean that you're going to see them in every place. So for instance, in the US, there hasn't been a total solar eclipse on the main 48 states since 1979. Not a total solar eclipse. And so it can be a long time between seeing these things. They're pretty rare events in any given location. So this is kind of another one that's showing you what's going on. I have the sun over here, and I have the Earth moving on its path. So this blue line is the path of the Earth's orbit. And here's the Earth, and here's the moon. And so if you're stood right under here on this little spot here, now you're not going to be able to see the sun from anywhere. It's going to be dark. If you're in this slightly lighter circle, you're stood here, you'll be able to see some of the sun. So it's a partial eclipse. You can't see all of the sun, but you can see some of it. And then elsewhere out here, everything looks normal. But you can also get that as the Earth is moving this way and the moon is moving this way, you get this spot is going to move across here. So you get a path that's drawn out. And you can also see just how small that is. It's about 60 miles across, which means that you really have to be in a fairly specific part of the planet that's when this lining up happens in order to see it. And what are we going to see? Well, when you get a total solar eclipse, the moon is exactly the right size to block out the sun. Remember, the moon is much, much smaller than the sun, but because it's so much closer to us, it's about the same size, apparently, so in angular size. And so what you get is the moon blocks out the main part of the sun, and so what we can see is this fuzzy glowing thing here, which is called the corona. This is always there, we just can't perceive it because it's about a millionth of the brightness of the rest of the sun, and so it's just too faint. We don't have enough... we don't have the dynamic range. We cannot perceive something so faint next to something so bright. We know this when we're out in the sun. It's hard to see things that are in the shade when it's really bright and you're out in the bright light, and vice versa. And so it's something that is to do with how our eyes adjust to seeing things at different levels of brightness. There are different types of eclipses. So you can see here, this is showing you what happens as the moon moves in front of the sun. So here you can see the moon is starting to take a bite out of the sun as it moves in front, and then it's got a bigger bite, and eventually it's blocking out the sun. But in this case, it's not blocking out the whole sun. In this case, you've still got this piece here that is sometimes called the Ring of Fire. It is an annular eclipse, and we'll talk about why that happens in a second. But you're going to see something like this, whether you get to see the annular or you get to see something where it's completely black here and then you get the fuzzy corona around it. But you always start with a partial that's getting more and more of the sun disappearing till it's almost completely gone, and then we've got it, the moon is moving back away, so we're starting to see the sun again. To understand why we have this issue of whether we get to see a full eclipse, a total eclipse, or an annular eclipse, or a partial, we need to think about the size of the moon. So the moon doesn't change in real size, its diameter stays the same, but we can see here that, in fact, its orbit is not circular, it is elliptical, it's a little bit elongated. And so when it's at its closest point, it's about 10% closer than when it's at its furthest point. And so it's going to look a little bit bigger, right? When you have something close to you, it looks bigger. When you have something further away, it looks smaller. And so what we have is a change in size that is proportional to the change in distance. So at perigee, it is 10% larger than at apogee, where perigee is the closest point to the Earth and apogee is the furthest point. And so you can imagine where when this is happening, when it's really big, it's big enough to block out the sun. But when it's really small, it's not quite big enough, and that's when we get the annular eclipse. I'm sure that many of you have heard of the supermoon. And basically, you know, the orbit is, so the moon is at perigee once a month, every 29 and a half, actually every 27 and a third days, and at apogee, at its furthest point, at the same time. But because there is a difference between how long it takes to go around the Earth and how long it takes to get back to full moon, that has to do with the Earth moving around the sun, so the direction to the sun changes. What happens is that you only get a full moon that is at perigee, or close to perigee, once a year, and that is the supermoon. It's when the moon appears biggest, because it's slightly closer to us than usual, and it's also a full moon. Now, if we take into account the Earth's orbit around the sun as well, that's also not quite circular. So you can see here, at this point over here, it's at its closest point, which actually happens in January, and it's at its furthest point on July 4th. And so what we have is something that you can imagine here. We've got the Earth is very slightly closer to the sun than usual, and the moon is here, it's slightly closer to the Earth than usual. So they're both big, and so you're going to get the moon blocking out the sun. You can imagine where you're at this side, and now, you're still on this side, that the sun is very large relative to its usual size. It's at its biggest point because you're closest, but now the moon happens to be at its furthest point when it lines up. And in that case, the sun is going to be bigger than the moon. Just to try and give you a more visual idea of what this looks like, here we've got how the changing size of the moon is. So the moon changes by about 10%, and that's because of the elongation of the orbit is enough that there's a 10% difference between the closest point and the largest point. The elongation of the Earth's orbit is not as big. It's only about 3 or 4%. And so the difference between when we're at our closest point and when we're at our furthest point is much smaller. So if you get the moon at its closest point and the sun at its closest point, then you get a full eclipse. But you can see here, if you get the moon at its smallest point, even when the sun is at its smallest point, you're not going to get a full eclipse. You're going to see a little bit left. And so that's when we get this annular eclipse. And sometimes you can have eclipses where they move in and out of that. So you've got something that is, the moon is not quite big enough, and then as we move around in our orbit, that changes the ratio, and you've got a full eclipse, or vice versa. So this is more or less a summary of what you're going to see. Here we've got the sun, the moon is at this point. If you're under that point A, you're on the little spot where you can't see the sun at all, and you get a total eclipse. If you're in this region B, which is called the penumbra, which just means the slightly less bright bit, that is where you'll see a partial. And remember that the full spot is moving, so you always go through a partial on the way to a total eclipse. This is what happens when the moon is a bit further away. The point of the shadow is before it hits the Earth, and in this case, if you're at this point, you will still see part of the sun, but it'll be blocked out in the middle, and you'll still have a partial in this region around here. Okay, so there's another point that I wanted to get to, and that has to do with how fast we move in our orbit. So this is showing the sun and the Earth, but this is true of any two bodies orbiting each other. And so as we go around, you can see here, when we're at our closest point, we're moving a little bit faster, and when we're at our furthest point, we're moving a little bit slower. You can think of it as being, the Earth is moving at a certain speed, and at this point, it's actually going fast enough that it can start to break away. It's breaking away from the gravity of the sun, but the sun's gravity is pulling it back, so it's slowing down and slowing down and slowing down, and eventually it can't win, and it starts to pull back in. But because the sun is pulling on it, it's speeding up and speeding up and speeding up, and it can start to escape again, and then it slows down and slows down and slows down. You can also think of this as conservation of angular momentum. You think about a skater, when they if they have their arms out, then they spin slower, and as they bring their arms in, they spin faster. As something gets closer into the center of gravity, it moves faster in its orbit. As it gets further away, it moves slower. Well, why is this important? Well, let's go back to our image of here's the sun, and here's the Earth, and here's the moon. At this point here, the Earth is moving at its fastest because it's closest to the sun. And the moon is moving fastest over here because it is closest to the Earth. And so what you have is that the time it takes, remember that the spot depends on how far it goes and how long it goes on that path, depends on the Earth moving that way and the moon moving that way. And so what you get is something that might only be about a minute. But if you're at the other end of the orbit, we're moving more slowly on our orbit. The Earth is moving more slowly on its orbit. The moon is moving more slowly on this side of the orbit. And so what you get is something that is then taking a lot longer, and it can be about 5 minutes. And so all of these things lead into how long it takes and how much you're going to see for a given eclipse. What this view graph is showing you is the eclipses from 2010 to 2060, so about 50 years from now. And the one that we really care about is here. But part of the reason for showing this is that you have to be under this path in order to see a total solar eclipse. Somewhere around it, you're going to get to see a partial. But you can see right here, we've got this 2017 eclipse that's coming. And there's also another one that runs right through the US in another 7 years afterwards, in 2024. So we have a couple of really great opportunities. But this is the one that's coming, and this is the one I'm going to spend time on right now. So I want to show you this. I want to say particular thanks to Javier Hubier and Jay Paskov, who I believe was the person who gave me this. And I'm going to show you this animation that he made, which is just a fantastic animation. So you can see the moon is starting to block out part of the sun, and we're going to start to see the dark spot where the moon is directly between the sun and the Earth. There we go. And it's kind of elongated because it's at an angle on the globe. But as it gets more and more direct, you get a spot. And it goes on to Oregon, and into Idaho, and into Wyoming, and into Nebraska, and into Missouri, and then into Kentucky and Tennessee, and into South Carolina, and out into the ocean. And so we can really see the path very well. I wouldn't worry about the times down here. We'll come back to the timing later. But what I do want to do is to make you watch it again, because I'm betting that everybody was just watching the dark spot. And so what I want to do is try and make it start again. Now watch the size of this big shadow. If you're under this big shadow, there is a partial. The closer you are to the spot, the more of the sun is missing, but it's still partial. You don't see a total. But you can see here that as it comes across, it covers the whole of the United States, the whole of Canada, and most of Central America. So even though only the states under this path here get the total, the entirety of the North American continent gets to see a partial eclipse. And so this is something that everybody's going to get to witness. And that's pretty cool. So this is kind of a close-up on that idea. And here you can see if you're under this bright yellow streak, this is where you will see a total solar eclipse. The contours on here show you how long you'll get. So you can see as you get towards this middle section here, you're getting longer and longer. It's 2 minutes 40 once you get to here, and it's only 2 minutes out here in Oregon. But you can also see that, you know, for most of the US, we're seeing 80 or 90% of the sun is going to be disappearing during this eclipse. And even down here in Southern California and up here in Maine, you've still got nearly 70% of the sun missing. So it's going to be a spectacle regardless of whether you're under the path. But the path is really quite spectacular. Now, I want to just bring that together with that idea of where the spot is. So you can kind of see here, here's the shadow and the spot moving across the US and how that relates to this image where we've got where it's full and how much of the partial you're going to see. This particular animation I really enjoy. It kind of shows you how this changes across the nation. So as it becomes total in Casper, and then in Grand Island, and then in Columbia, and then in Nashville, and so on, you've got how it's changing across the path. But you can also see that down here in Albuquerque, or down here in Dallas, or down here in New Orleans, you've got a view that's really going to be quite impressive. And so even though these places are not on the path, they're still going to see things. But you also get to see how it's changing along the path. And this is showing you why it matters how close to the center of the path you are. So the shadow is circular. And if you're near the center of the path, you're under the shadow for longer. If you're at point 1 near the edge, you're off the path. You're off the shadow much more quickly. And so it's really good to be close to the center of the path. Now this is a close-up on Missouri because I live in Missouri and I am planning events for Missouri. I can make more of these for other states if people would like me to. And here you can see I live in Columbia. University of Missouri is based in Columbia, and so this is where we are. And you can see that the longest actually goes through Marshall and Boonville, and then somewhere between Columbia and Jefferson City. I think it's actually somewhere in Rockbridge State Park or maybe in Three Creeks. But even where we are in Columbia, it's at 2.5 minutes. So we're still going to get a full 2.5 minutes. And I just want to point out that this is from greatamericaneclipse.com. This is Michael Zeiler's website. It's fantastic. And so you can really see in detail where different things are. I want to break that down to just a little bit more simple. Oh, before I do that, I just want to point out it goes right through St. Joe, and I know there's going to be a big event in St. Joe. It goes through Cape Girardeau and these parts of southeast Missouri. It goes through southern St. Louis and northern Kansas City. It doesn't go through the downtowns, but it does go through most of Forest Park, and I'm sure there'll be fun events there. So this is a simplified version where you can see again, here's Kansas City. The red lines mark the edge of totality, and then the blue line is the midpoint, is the midline. This is where you'll get the longest. So you can see how close Columbia is, but here you can see the counties. So if you live somewhere out in the middle of nowhere, you can figure out where you are. And if you're out at Moberly, you're going to get a short duration because you're near the edge. But if you're in Columbia, you get almost the longest time. Now I want to show this. So this was made by a friend who is also a great artist and an astronomer. Tyler Nordgren. He has his own website where he has some of these, where he's making posters for each of the states on the path. And I asked him to make one for Missouri that was based on what the university looks like, and so we have this lovely poster, and I'm hoping that we'll be able to make him some money with this at some point soon. But he's making posters for the whole path, as well as ones that account for the whole country. Now, I just want to take a step away from pretty pictures and talk about what we're doing, because there's a lot going to be going on. This is going to happen on August 21st, 2017. That's the first day of classes for the University of Missouri. It's a Monday. It's also the first day of classes for the local schools here in Columbia. And so we want to make sure that everybody gets to see it and that it is very easily and safely viewed. So right now the plan is that we will have a viewing event at Faurot Field, that is the University of Missouri's football field. I expect that we will also need some other sites, thinking about using Traditions Plaza, which is one of our quads on campus. Maybe if the city will let us, do something in one of the parks, maybe Stevens Lake Park. I'm trying to facilitate various organizations in helping with this. We also have to have safety precautions, so you should never look at the sun without protection. I think most people know this. You don't look at the sun, it hurts. And you will actually do damage. And so if you want to view the partial eclipse, that is anything up to it being completely and utterly darkened, you need safety precautions. Even if you want to watch an annular eclipse, you can't look at it without safety precautions. It's so bright, even in that tiny bit that's still showing in an annular eclipse, that it's too bright to see it safely without precautions. Typically the way people view it is either using a pinhole camera, so I'd like to develop some kits for teachers so that people can start to make those for themselves. There's also now fairly cheaply available eclipse glasses. We'd really like to have people get them for free. I'm still working on that. And you can also use some welding goggles, but you have to be really careful because the spectrum of the sun is very different than the spectrum of welding, arc welders and acetylene welders and all that. And so the protection is not quite the same. And so you have to actually go up to a number 14 or above. There are various websites that are very good at helping you to figure this out, and there are places that you can buy eclipse glasses. Preparing the citizenry. I want everybody to know about this. I want people to be having parties. I want to make sure that all of us that are professors are ready to have their class go outside and incorporate it into their classroom. We've got to pay for it. There's going to be some costs involved in this, so I'm still working on how we do that. There's going to be some fundraising needs to happen. Nationally, the whole country gets to see this. Even at the furthest extremities in Southern California and Maine, it's over 65% eclipsed. If you're close to the path, you're going to want to come to the path. There are 20 million people live under the path, and there are about 500 million people under the whole partial eclipse. And so we want to get people excited. We want to have TV campaigns. I'd love to have a Mythbusters on when it's safe to look at the sun. We want to work with the medical community to get out the information, because the last time there was one in the US in 1979, there was a lot of misinformation and people were scared to look at it. It's not dangerous, but you do have to be safe. And there are ways to look at it safely, and we want to make sure that that information gets out there. And I want to finish now, I'm not going to show you that, I want to finish now by showing another video. Now this one comes from Michael Zeiler. I believe it's available on his website. I want to kind of guide you through this. I actually got this one from Jay Pasakoff, who is an eclipse expert and has been a wonderful resource. Before I press play, I want to explain. So this is this elongated shadow, so it should be a circle, but because you're on the curvature part of the Earth and it's out in the ocean, and this is the time in different time zones. So for us in Columbia, Missouri, it's a little before noon local time, and this is what it looks like out in the ocean. And as it approaches land, it's also getting towards being directly overhead, so it's it's going in front of the sun, and so it's getting more circular. We get landfall in Oregon. It goes over Salem. It goes over eastern Oregon, which is desert, probably good for weather. Then it heads into Idaho. I don't think there's very much in Idaho, but it does go over Idaho Falls, which is a big town. Then it goes over the Tetons. You can see Jackson there. It goes over Lander. The University of Missouri has property in Lander. It goes over Casper. I think there's going to be some cool stuff going on there. And then it heads into Nebraska. And you can see it goes over some smallish towns. I know people at University of Nebraska Kearney are going to be doing things there. Also goes over Grand Island, and Lincoln gets it for a short time. Teeny bit of Kansas, but we don't care about Kansas. Into Missouri, and you can see that it comes over, and there it is, we're in Columbia, woo! Okay, and then it heads out, and it goes through southern St. Louis, and through Cape Girardeau, into a bit of Illinois, a bit of Kentucky, and into Tennessee. You can see it goes right over Nashville. Vanderbilt is in Nashville, another SEC school, so I'm happy there. Then into a bit of Georgia and a bit of North Carolina, into South Carolina, and this is the thing that makes me happy. Columbia again! Another SEC school in another Columbia, and off it goes over Charleston and out into the Atlantic. And you can see here we've got the names of Michael Zeiler, Fred Espenek, who's a very famous eclipse person, and Javier Hubier, who is just a fantastic eclipse person. And that's all I have. I hope that you've enjoyed this and that it has been useful. And if you want more information, you can go looking at thegreateclipse.com. There are all sorts of other sites too.